Hi everyone, in today's video we're going to go over the halohydrin formation. So the way I like to remember just what we're dealing with in the first place is halo is going to be half of halogen, and hydrin is like hydrate, it's involving water. Or compounds that are like water, so compounds with an O and an H typically. So this can include ethanol, methanol, but mainly you'll see it with water. So the general sort of reaction that we're dealing with is an alkene, just a standard alkene with a halogen and water. So what is this going to produce? It's going to give us a Markovnikov reaction where OH ends up on a more substituted carbon and the halogen ends up here, and we're going to usually have HX as a byproduct of this reaction. So just to make that more clear, if we have a chlorine and water, we're going to end up with a product that typically looks like this, with OH here, chlorine here, and an HCl as our byproduct. So let's go through the general mechanism of what's happening here. I'm going to take this alkene right here and I'm just going to turn it on its side. So let's say we're looking at it more like from this angle, and we have this going out this way. So what's going to happen is it has a double bond. Instead of X, actually, I'm just going to write this as chlorine. So Cl2 looks like this. What's going to happen is this bond is going to attack the first chlorine, push the bond onto the second chlorine, and the chlorine is going to attack the bond back. So this is going to form a sort of cyclic chlorine intermediate, and obviously we're going to have this chlorine ion by itself. And you'll notice that this is a cyclic intermediate, so it's taking up one whole face of the molecule. In this case, I've drawn the face as pointing up. This face could have also been drawn pointing down. So the chlorine could have attacked from either side. It could have attacked from the top side. It could have attacked from the bottom side as well. So this is the bottom attack and this is the top attack. So what's going to happen after that is, typically if you've dealt with purely Cl2 alkene reactions or halogen alkene reactions, you would know that this second ion is going to usually attack from the back side or the front side and eject the bonds in either case. But that's not what happens here. If you're not familiar with that, just ignore that. But usually, actually, what happens here is water takes over. So in our example, we'll use water. Again, different things could be involved here, like ethanol or methanol. But in this case, there's way more water than there are other chlorine atoms that are formed. So in this case, water is actually going to react first. And water is going to attack the more substituted carbon here, and it's going to expel the electrons onto the chlorine. Same thing here, water is going to attack the more substituted carbon and expel the electrons onto that chlorine. The reason for this is one of these carbons is going to become more electropositive as the chlorine shifts away from it, and we'd rather have the carbon that's more substituted be the one that's more electropositive. So that's why it's going to attack the more substituted carbon. So that's going to give us a product that looks something like this in either case, where the chlorine and the oxygen are opposite in terms of their stereochemistry in either scenario, and typically we're going to end up with a racemic mixture of products because it's going to form in either way, right? Either from the front or from the back. So that's the general mechanism. We'll move on to some examples, and hopefully that will make stuff more clear. So here's our first example. We're going to pay attention to stereochemistry this time. So immediately I recognize that I have Cl2, right? I have a halogen, 2 halogens, and I have a water as well. So those are immediate clues that this is going to be halohydrin formation. So what's going to happen? Okay, well, we know that the alkene is going to want to attack the Cl2, push this electrons off, and the Cl2 is going to attack back. That's going to give us this intermediate, this cyclic intermediate here. In the first example, I'm going to imagine that Cl attacked from the top. So these are going to be wedges, and I'm going to imagine that it pushed this methyl group to the back. Another obviously equally likely scenario is that the Cl actually attacked from the back and it pushed this methyl group to the front. So either scenario here is okay. Now what's going to happen? Well, we have water in excess, right? So water is going to attack the more substituted carbon and push the electrons off. In this case, though, water is going to attack from the back, so we're going to get a product that looks like this for now, with the Cl here. And the methyl group should also face up, because when the water comes in from the back, it pushes the methyl group up, as well as pushing these electrons onto the Cl. And in this scenario, we're going to get sort of the opposite, where water is going to come in from the front, going to push the methyl group down, and it's going to expel those Cl electrons. So I'm obviously not gonna write out the deprotonation step for both, since they're the same, but for one of them, what's going to happen is another water molecule is going to abstract this proton, and the electrons are going to move back onto that oxygen. So that's how we get our final OH products. So we're going to have this OH here, Cl, and the same thing is true for this guy, just that this will become an OH instead. But stereochemistry wise, these are our final two products. Okay, let's go to another example. So notice here that again we have a halohydrin formation going on, but that both of the carbons are equally substituted. So in this case, the oxygen of H2O won't have a preference which side it attacks. So in the first scenario, let's say that Cl2 forms a top face cyclic compound that looks something like this. And in another scenario, I will call this pathway 1. In another scenario, it forms a bottom face cyclic compound, pushing these methyl groups up. In either of these scenarios, when H2O comes along, it can attack either this face or it can attack this face. Same thing here, it can attack this face or it can attack this face. So we're actually going to get 4 products at the end of the day. So our first product, I'm going to call this product 1 in purple, is going to be our original here. And since OH is attacking here, it's going to attack from the bottom. It's going to push this methyl group up. It's going to attack from the bottom. It's going to become an OH. It's going to push these electrons off. So the Cl is going to exist here, and this methyl is going to still be going down. In the second scenario, which I'm going to say when OH attacks this carbon, draw that as number 2. We're going to have obviously everything else on this side of the molecule be the same, except now the OH is pushing the methyl group up on this side. It's going down on this side of the carbon. It's going to push the electrons onto the Cl here, and the methyl group is going down there. In the third example, we have OH attacking this version. In that scenario, we have a molecule where OH is coming from the top, pushing the methyl group down, and Cl is going to stay down, and the methyl group is going to stay up here. And in our final scenario, OH could be coming here. What happens then? Well, we have our molecule. OH is going to come again from the top, push the methyl group down. Cl is going to be still going down, and the methyl group is going to be facing up. So in this case, we're going to have 4 products, and that's because, again, neither of these carbons are more substituted than the other, so that's why we get 2 pairs of attacks from the water in each scenario, and that's why we end up with 4 products. So you may find these problems tricky on exams. Professors may like to trip you up by giving you carbons that are equally substituted. So in those scenarios, you really want to look out for all these different possibilities. And we'll go on to a last sort of example. So again, we can recognize this is halohydrin formation. In this scenario, again, the chlorine is going to have a concerted attack with this alkene. Going to attack. Alkene attacks back, pushes the electron off. Okay, and then we have 2 possibilities. The first possibility is that we formed a cyclic intermediate on the top face. The second possibility is that we have this same molecule, except we just formed the intermediate on the bottom face instead. After that, we have water coming in. And again, water is going to attack from the opposite side onto the more substituted carbon. So in this case, the more substituted carbon for each is going to be here, and it's going to be here. So in this case, water is going to attack from the bottom, pushing these electrons up top. In this case, water is going to attack from the top, pushing these electrons down here. So our final product should be, in this scenario, we should have an OH on a dash, and we should have Cl here. I'm not writing stereochemistry for this Cl since it's not a chiral center. Remember that there are 2 hydrogens here, so there's not 4 asymmetric attachments to the carbon. So I'm not going to write stereochemistry there. And on this side, the OH is going to come from the top, so we're going to get on a wedge, and the Cl again here. Okay, so I hope that covers the basics of halohydrin formation. Please leave any questions down in the comments below, and I'll see you in the next video.